So we have two items on our agenda today. One is the Triton CPU update, and the other is the Intel update. I think Minjang is not yet here, so let's start with the Intel update, and then we can do the Triton CPU update later.
Ilya is here, so Ilya, Minjang is not the only lead on the
Okay.
project.
Okay, he
Well,
said that he
Minjang
would
has the
share some
presentation with the general
slides.
status update, and he has his portion of slides, and I have slides for our research of softmax case, so I can start with it.
Yeah, you can get started, Ilya. Sure.
Okay. So I'll show the results of our work on Triton CPU for softmax, and then hopefully Minjang will join and give the rest of status update. So can you see it? Okay.
Yes.
So we were investigating softmax performance in Triton CPU. Functionally, we enabled it like a few months ago, but only now we got to its performance, and I tried to run it on Software Rabbit's machine with 2 CPUs. We locked frequency and disabled hyperthreading for more stable multi-threaded performance measurements. And as a base, we used tutorial kernel and compared Torch Inductor native and Triton performance. So our starting point looked like this one. So this is a single-threaded run just to look into the quality of code generation. And you can see that the best performance is shown by Torch Eager mode. Then we have Torch Inductor and Triton. And one of the problem clearly visible here is that we have this constant performance drops depending on the row size, and it drops like twice each time we cross a boundary of power of 2. And this happens because the way kernel is written and works on blocks of power of 2 size, and if row size exceeds power of 2, we round it up to the next power of 2, and therefore we just might spend a lot of time doing a useless job that is not then stored. And we can fix it by tiling loops, and in this case, we won't be working on a like maxed out data. And several months ago, we decided that tiling and loop fusion is out of Triton CPU optimization scope, and it should be done by users. So here we modify softmax kernel to use tiled loops. Since softmax has a couple of reduction in the resulting kernel, we get 3 tiled loops, and performance of modified loops looks like here. So here we don't have any performance drop, and it becomes smooth and stable. The problem with writing tiled loops is that while we write them, we might need some temporary tensors and some place to store them. And when I modified the kernel, I simply used output buffer as a temporary memory. And actually, native Torch implementation does the same, and Torch Inductor implementation locates a couple of temporary buffers. But here, overall, the problem is that Triton doesn't provide us the facilities to locate such scratch tensors that can be used to store temporary values. And this needs to be solved somehow for Triton CPU. So possible options are to use tensors in some kind of insert extract operations. And as far as I could see, there is no currently operations in Triton to like insert and extract subtensors. So now it's not an option, and also there is a limitation on tensor sizes. So size should always be power of 2 and should be statically known. And in our case, when we have a tiled loop, we don't know the total size that needs to be stored. We can also use user-provided buffer. Like in our case, we used output buffer. And like if you look into inductor-generated kernels, then it also uses buffers allocated externally. So this option is available right now, but it's not really user-friendly. So probably it will be more convenient for users to allocate some sketch buffers inside the kernel. So we should think about providing such API. We should think carefully about which options to choose, and I think we will discuss it in more details in the upcoming Triton CPU meeting. So even with this modified kernel and more stable performance, we see that it doesn't really increase performance dramatically. So we are still like 5 to 6 times behind the Torch native implementation and about 3 times behind Inductor. And we analyzed the kernel and found several problems. So the first problem is that we use scalar math functions from libm, and for better performance, we of course should use vectorized math functions. We chose to use libmback, which is a set of mathematical functions used by OpenMP. It provides all basic functions in different variants for AVX 512, AVX2, and SC extensions. Another option is to use Leaf library. This library is used by PyTorch, and we also added the option to link kernels with Leaf library and use it. But I didn't see any performance differences comparing libmback and Leaf library. So I think the default might be libmback because it's available on like all machines. So another problem we solved is optimization of pointer arithmetic for scalars. The problem is that in our kernels we compute tensors of pointers, and then if we detect that load can be vectorized, we simply extract a scalar pointer. And usually LLVM does a great job. It detects that vector code can be optimized and optimizes it into a scalar pointer computation, but in some cases its optimizations fail and it really computes a tensor of pointers and just extract a single pointer. So we changed a little bit our code generation in MLIR to avoid it. Next step was about reductions. We initially used high-level vector dialect reduction operation for multidimensional reduction, and it works great, but the resulting code it generates is not always perfect. So like when we have a single vector left and we need to perform this horizontal computation over all vector elements, then existing logarithm simply uses scalar instructions instead of shuffles and vector instructions. So since that time, we actually added more generic support for scans and reductions using lower level vector operations, and using them by default gives us performance gain here. And the last optimization we used is optimization of masked loads and stores. In our tiles, we use masked loads and masked stores, but in fact, tensor size is usually is divisible by a tile size, so it can be optimized out. And right now, we detect patterns of such tile loads where total tensor size is divisible by tile size. And we use divisibility hints for that. Unfortunately, right now, divisibility hints are limited by 16, so we still size more than 16, this optimization cannot be used. So we might change divisibility hints behavior to provide like more divisibility hints when it's not 16 divisible, but 32, 64, and so on. And another option is to use a more generic approach and just peel out the last loop iteration to get rid of masks, at least in the loop. So here is the result with all optimization applied. Triton 1 is in orange color. So we see that we're pretty close to the torch here. And this is still a single thread. So when we move into multiple threads, the situation is a little bit different. Here we be still behind torch, which shows better performance on all sizes. And I was profiling this code, trying to understand why these kernels behave like differently from torch, because we basically generate very similar code. And it appears that we have quite significant overhead on each kernel call. So here I profile with vtune and I set ITT tasks just to see how much time we spent in Python. So this first task, run kernel, wraps Python kernel call, and kernel launcher task is a task in our driver. So the time starting from the kernel call until we get into the driver is about 50 to 70 microseconds, which is quite significant compared to the total execution time. And we need to understand what's going on there, why we spend so much time in Python, and try to optimize this out. So if we just pretend that we could beat this overhead, that projected performance would be quite similar to the torch. So here we just pretend that we could reduce this overhead by 55 microseconds, but for now, we don't know if it's actually achievable. That's all from my side. Minjang is here. So Minjang. Sorry, probably someone have any question?
Yeah, yes, I have one question. So this project, the torch native, the orange line, is it using 1DNN as a library or not?
No, as far as I could see from the profile collected by vtune, it uses its implementation of softmax written in C++.
Okay, thank you.
But it uses pretty nicely optimized vector code. Any more questions?
So does this mean so after optimization it's better than the torch inductor version or no?
Well, our current status is this solid blue line, so it's not better. But it's worse. The only reason why it's worse is this overhead that we have. It's a constant overhead that we have on each kernel call. So if we use like bigger inputs, then this might become negligible and we wouldn't have any performance difference compared to torch, but we measure softmax kernels on pretty small input sizes and it becomes significant.
No, I mean the torch inductor one, not the torch in native.
Torch inductor. So no, yeah. This one torch native. Torch inductor is actually quite slow. Here's this. Here's it is on multi-threaded. It's actually the worst one.
Oh,
and the reason for that is that it distributes workload differently compared to Triton and Torch native. Instead of like splitting workload into set of rows and processing row by row. It like splits the whole softmax into 3 phases, like this maximum element computation, then exponent and sum computation, and then scaling. And it computes the stage by stage for the whole tensor using 2 intermediate tensors. It creates like worse data locality, it creates some sync points, and therefore overall performance is not so good. Okay, if there are no more questions, then Minjung, please go ahead.
Yeah, thank you, Leo. I mean, taking the first thing out. Yeah, okay. So let me share the screen. Okay. Right, just to make double check. Oh, yep. Can you see the my slide?
Still loading for me. Oh yeah, I can see it.
Okay, good. Thanks. All right. Yeah, this is Minjang from the Meta. So yeah, thanks for the Ilya for the first presentation, and this is the more like a bit more general the Triton CPU update that includes both the Intel and our Meta work. So yeah, let's just start with the summary first. Just one word. So far so good. I think that we are on track. Yeah, and yeah, so we didn't see any major issues in general Triton CPU development. So we are happy about it. So both the Intel and the Meta right now, so we are actively working. So we have around the 4 engineers right now. There was also PhD summer intern from the Meta, so he worked for the ARM side. So, so this is so our internal goal, but maybe also important milestone for the general Triton CPU in the open source community. I would say that the first goal is that the feature completeness. So the meaning of the feature complete is kind of vague. So we set up a couple of bars. The first one is the test coverage. For example, there is the test core in our Python, the Triton upstream suite. Right now, so we are having like 96% of the coverage. So some of them are there are a few failing, but some 3%, 4% are mostly skipped because they are taking too much time. So I will discuss later. But in general, the coverage at this time, the basic coverage is pretty good. And we also now looking for the torch inductor. So using the Triton CPU is a torch inductor backend. So then that allows us to use the torch inductor test suite for the much better test coverage. So I think this is another very good target to verify the Triton CPU the feasibility. And we have another, so internally we have another goal. So now we have some demands for the Triton CPU for the internal usage. For example, the Edge or some other PyTorch Edge on the devices on a phone. So yeah, there will be some important kernels, and we want to also run those kernels using the Triton CPU with a decent performance. The status is pretty interesting, pretty good. So now we can run the general the GenV, the vector or the gem on both x86 and the ARM architecture. And if we are using the fast math, like the aggressive optimizations, so we were able to achieve sometimes better performance on the ARM or the similar performance on the x86. And as Ilya showed the softmax, so that's similar, right? But once you did some better optimization, like a loop tiling, tiling, then the perf is also pretty similar. Okay. So we know that, right? So the overall approach of the Triton CPU, yeah, it's obvious. So using the SIMD and the OpenMP. And yeah, so we are the most important decision for the Triton CPU is that we are using the vector MLIR dialect. So that means that we are converting the most of the pretty much everything, the TTIR operations and the types to the vector types and the operations in the Triton CPU IR. I mean, some of them are still leave until the later phases, but the most of them are lowered to the vector MLIR. The backend part, so we are using the default LLVM, the code generator, which means that the ones we have the vector representation in LLVM IR, all the actual physical vectorization are done by our LLVM backend for both AVEX 512 and the Neon. That doesn't mean that we cannot generate our handwritten vectorized code. It's still possible, obviously, right? So one of the example I will show that the Neons, so we can use the Neon's BF dot, which is a specialized instructions for the BF16 dot operations. So that was one of the very good example how we can add our own manual vectorization for the better performance. Yeah, just another quick overview, very quick overview. So this is the execution model, so we know that, right? So we are using the OpenMP plus the CMD. So say that this is the very simple 32-bit vector addition of a 511 elements. So that means that we are going to use the AVEX 512 register because if you set the block size about 128, so each AVEX 512 register can take 16 elements. And the block size here, it means that each program or the PID processes, programs are taking the 128 elements. So that means that we need the 8 register. And that means that we need 4 the program, the Triton program or the PIDs. So that is launched by our OpenMP parallel for loop. So this is our overall execution diagram. So the entire the vector is divided up to 128 the width, and that this is shared by the spread across the OpenMP for loop. So yeah, that's our recap of our execution model. So this is our the current Triton CPU compilation stage and the launching. It's pretty similar to the GPU side, but so we have a bit more specialized routines for the CPU. So basically TTIR, that is the same thing. When we have a TTCIR, so that is the most important part in our Triton CPU world because we are rolling to the vector MLIR. Just a minute. Okay. Yeah. Then there is so we recently introduced an interesting stage, so which we call target specific TTCIR. So at this time we don't have that much routine here. The reason why we have this is that some of the operations that are only for the AVEX 512, some of them are only for the Neon. Yeah, so we want to have some a bit more target specific behavior in here, but it's not like we don't need to the fork another backend. That's not necessary, right? But sometimes we want to really have some very specific for the CPU. So that's why we have this TCIR. Okay. All right. Then the make LLIR is the same thing. And so when it comes to the lowering to the binary, so at this time, so now we are using these static compilations. So once we have the LLVM so we are actually statically compiling to the .asm text file. And we also create .so dynamic library in the this step. So when you look at this is our the Triton the cache directory. So you can see that .so is also staying in the same cache. So this was actually better for the whatever the debugging and the better cache management. The launching is also similar to the GPU. There is some the template code in the OpenMP, the C++ code in the driver.py, and the driver is taking the this.o or .so and find out the function pointer. Okay, so this is the quick overview of the what is the steps, what happens in the TTIR to the TTCIR. So as I did before, so we are trying to convert most of the tensor-based types to the operation to the vector dialect. And then we don't want to have the tensor types in the TTCIR. So there was some design discussions with the Ilya and us. And our argument is that, yeah, it's better to have the consistent types in the TTCIR for the better, the clean, the architecture. So that's the design decision. So here are some examples. The make range, this is one of our key the operation when you build up the pointers, right? For the GPU, because it's handling the scalar and just a couple of the scalar, not too many scalars, right? So it does not need to handle entire range. So, but in the CPU world, so we need to generate really just the constant in the index from the from the 0 to the block index, block size. So it's quite different. TTL load is also very different. Yeah, so when it comes to the GPU world, it's basically generating the scale operations, but of course there is also the vector load and the vector store for the GPU, which is it's not really the same to the CPU, but they do have also their own vectorization. But here the CPU world is pretty different, right? So we are using the access info to get the contiguous the contiguity and the stride information to get the vector size. So once you know the vector size, so we are lowering to TT.load operation to the vector, the mask load operation, which is taking memory reference type. So similar, so reduction is also lowered to the data vector reduction at this time. There is some interesting cases of vector the Triton print. The print is pretty simple, right? But it turned out it's a bit tricky because so we don't want to have tensor type in the TTCIR. So there were a couple of the trade-offs here, but it was better to introduce very simple Triton CPU print that is intermediate step that is only taking the primitive types and the vector type, not the tensor. So that was better for the later phases because we don't want to keep the tensor types in the later phases after TTCIR. Yeah, this is also the recap of how the pointer arithmetic is done in the TTCIR. So here, yeah, the GPU is identified for it's most of the scalar types. Yeah, of course, this can be vector in most of the 4 elements at the same time. But the CPU, yes, here, if the block size is 128, you need to create actually the constant array for the make range here. Then you do really just the integer arithmetic to compute the pointer array in the integer 64. Then, but the problem is that our vector load are taking memory references. So now that we have the array of the pointer, right, integer, so there is somehow we need some circles how to convert those the integer pointer to the actual memory references. So here at this time we are reusing our Triton integer to PTR, that is a Triton ops. Then we have another specialized Triton CPU ops, which is converting to the pointer to the memory references. So that's how we are generating the TTCIR in the basic important load and store. Okay, and the later phase in the GPU world, this is a place where the most of the interesting things are happening. But at this time, due to we are using the vector MLIR, At this time, it's the TTCIR to the LLVM. It's a bit more simpler than the GPU side. So yeah, so there is a 2 example. Program ID. So we are passing the program ID as the additional arguments to the opponent from the OpenMP loop. So they are just reading the argument here. So in the CPU, there is no any like a CTA, whatever, registers, right? The TID, something. So that's implemented in this way. Load up operations are, so we already lowered for the vector types, vector loading in the TTCIR to the vector masked load up. So that's already done. But there is also for the cases. So if we cannot lower to the vector load up, there is still scalar TT load. So in this case, we are just, this is the worst case. I mean, we should avoid as much as we can, but this is lower to the LLVM load up. So yeah, there is something final lowering is happening. Another difference is from the GPU side. So we are having the fine-grained pipeline. In GPU, probably you have seen that there is just one big gigantic packet for each lowering. For Triton to Triton GPU, really there is just one big path. Yeah, and here there is a lot of the populated, lots of the paths, right? The same thing happens in the also Triton NVIDIA or the AMD GPU to the LLVM. So there is 2 gigantic pipeline. But here our CPU world. So we went to much more fine-grained the pipeline. So individual, there are many patches like this one. So for example, the Triton to Triton CPU. So we have actually different the pipeline stages. I mean pipeline the entities. The better way is that it is actually easy to debug. So you can easily just on and off one of the pipeline. Yeah, so that's one of the major benefit, I think. And yeah, so but I don't think this is too much divergence from the GPU world. At the end of the day, so you still have the matching rewrite into the up conversion, the clashes. So they are still the same thing. So those pipeline is mostly how to pack it together. So this is just the packaging issues. Yeah, I don't think this is the major difference from the GPU and the CPU, but so in the CPU world, so we are trying to another approach. Yeah. Okay, as I said before in the TLDR, so we are also wants to use the better testing coverage. So for that purpose, we were thinking the torch inductor can be very good candidate. The PyTorch inductor generating a ton of the templatized the Triton code. So lots of the more crazy cases. So torch inductor can take arbitrary, the new backend pretty quickly. So we recently we tried the Halide as a PyTorch inductor. So it was able to be done pretty quickly, the same thing. So we hooked our Triton compiler, Triton CPU compiler for the torch inductor backend, so that we can test a lot of the torch inductor testing cases. We just started this work, and yeah, so there are many failing cases due to the unimplemented lib devices cost, and there are also many type mismatches. Like there is the built-in unrealized the theft that is usually happening if we didn't match the types. Yeah, that is usually one of the major failing cases. So I think this is a pretty good milestone where we can make some goals to make the Triton CPU more robust in many workloads. Yeah, another important issue is that so we want to syncing the upstream the Triton occasionally. So we don't have the strong rules, but my kind of rule of thumb is that whenever there is a LLVM hash update happening in the upstream, so we can follow the latest Triton upstream. The good thing is that the most of our Triton CPU code is isolated in the third party under CPU. So we didn't see that that many merge conflicts. So yeah, so that was usually okay. So that was a pretty good thing. And yeah, so that's why so we wanna keep the as much as we can. We wanna keep the consistency with the GPU. For example, the naming convention. I mean, it's not thoughtful. It's actually pretty important for me. So yeah, we do our best to keep the consistent with the GPU. Sometimes often the Triton is too much the hard coded for the only for the GPU side. The one of the major case was the auto tuner. So auto tuner and the do bench at this time they are hard coded for the CUDA case. So in the CPU the Triton CPU, I manually just change something for the working for the CPU as well. But when it comes to auto tuner, there will be a bit more some big changes. So we are proposing right now the better way how to make the auto tuner to be the device agnostic. So once we implement upstream the first, and we can also on the backport to the Triton CPU, which will make it much easier for the merge and the future of training. All right. Yeah. So a few more slides. Now this is more like the perf side issues. Okay. Yeah. So okay. So one of our major concern from the beginning is that the quality of the generated code from the LLM backend. So far, it turned out it's pretty good. Of course, there is some the inefficient cases for the reduction, but I will tell you later how we can fix this issue from the using the fast math optimization. But okay, let's look at the very simplest case here, the vector addition here. So we have the block size of 128, the same example. So that means that we are going to use 8 the registers, the GMM registers, right? So this is the how did the LLM generated the code. So simplest one first. So yes, there were 8 the vector at the packed single precision. So yeah, it's very beautiful. The 8 the vector addition here, followed by 16. 16 the load and load because we are loading the 2 vectors and also 1 vector store. So that is also ended up 8 that moved here. The same thing. So here, the generating the 8 the mask here. The very first time that we need to build the make range, right? Integer array. So that is done by the vector packed OR operation. The why OR because the very first time this was addition because we are building the make range from the 0 to 1 to 7. Then we do addition to the block ID from the base pointer, right? So they can be optimized to using the OR operation, because it doesn't print the same result. So so when it comes to simplest code, yes, we were able to get the very clean optimized code from the LLVM. But anyhow, so during my study, so I found out, so what if we have the compile explorer for the Triton? So so that's another maybe interesting intern project or some side project. So a bit more perf study from here. So in general, the block size, larger block size is better. It's not surprising, right? So we want to give the more job for each iteration for the OpenMP because there is overhead in the scheduling. So Ilya also showed it, right? So for the vector addition, so we are testing pretty different. It's a medium size of the vector, and I changed the block size. So so once you reach some like a 4K or the 8K, the block size is again the block size means that this is number of elements. Okay. So now the perf is pretty similar to the torch implementation. So so that's our observation. But one of the downside here is that if you increase the block size much larger, there is a problem in our the backend, the LLM backend side. So for example, if you are giving me like a 64K block size for this simple vector addition, there were crashes in the solution deck in the backend side. Also, the compilation time can be really long. So this is usually happens when it comes to GEM or the GEMB cases. The 2D cases, and if one of the sizes block size is longer than some certain threshold, the compilation time can be actually 5 minutes, 10 minutes, or something. So yes, we need to also take a look at this issue. Okay, I want to briefly present our the PERF study. So we the GEM is also working using the dot operations, but here is a simpler version than the GEM, so which is the GEM-V, the matrix, the vector multiplication. It does not use the TL dot operation, but it uses the TL sum, which is reduction here. And here, the multiplication is done by the element wise. So that is a good, pretty exercise how we can optimize for this the reduction cases. So this is how the algorithms are working in the Triton kernel. So basically we are chopping down the block size here, and we do so element wise here, and that we do reduction. All right. So it turned out fast math optimization was really important. So this is our the implementation here. So if you are passing from the Triton fast math, the one environment variable, it will enable this the optimization. So basically, okay, so this is our LLVM AI here. So once you turn on this fast math, basically, the only change is putting the association flag. So that means that, okay, compiler, yes, you can do very aggressive optimization. Without this one, this the reduce for the vector type is basically just scalar type, because we need to observe the associativity, right? So it was the generated code was the V at scalar f. It doesn't even use the GMM register. It was pretty bad. But once you pass this one, the code is really great. Just the one, the memory load, followed by the fused the memory addition, multiply addition. It's really just this is the kernel, the innermost loop. So here is my experimentation. So we tested on the old, pretty old the Skylake, the genome, and this is the matrix vector multiplication, and we turned on the fast math, and it was using the fused math operation. So so it was pretty good. So we were able to match the perf to the Triton CPU and the Torch CPU side. But one of the caveat here, at this time, the math thing is not working. There is some compile errors here. So the MLIR issues. So we were going to fix it. But at this time, the size is just the multiple of the vector, the block sizes. So this is also good. And we also compared with the Torch that the NN linear, so which is more close to vector of the GEM-B cases. So where we also found that the perf is pretty similar to each other. Okay,
So
now this is the
Minjang, I just wanted to interrupt. Sorry about that. But we do have the Intel update, so I'm not sure if you have a lot of more content or the Intel update is short.
Okay, it's short. Just 2 more slides.
Okay,
thanks.
sounds good.
So we also did some BF16, the GEM-B optimization for the ARM side. In the ARM, there is a BF.16 special instruction for the Neon. So we added the path, the transform passive. So basically we converted the sum followed by the multiplication into the BF dot. So this is the intrinsic we used. So the perf was actually better than the Torch. The reason is that we believe that the ARM implementation on the the torch inductor implementation for the ARM may not be optimized like the Intel. So that's why we were able to get the better perf here. And we also compared with the open source XNN pack. So yeah, this is everything is handwritten and the native code is similar. So smaller sizes. Yeah, so we have some high launch overhead here, but when the input size is larger, the perf also becomes pretty similar. This is also on the ARM side. Okay, so this is our final recap. So basically, so we want to short-term goal in this year is that, so we want to complete our testing coverages and the torch inductor, and we want to support more precision like a BF16 for the APX 512 using the BF federation, and we want to also support the auto tuning for the Triton CPU. And the memory layout, this is an interesting topic. I don't know. I think a linear layout can be a candidate, but I also saw that upstream there was some perf issues in the linear layout. But yeah, we will take a look at later. Yeah. Otherwise, yeah, pretty obvious. We wanna ramp up with the better perf and the testing coverage. But finally, yeah, the compilation time was kind of some problem when it comes to bigger block size. But otherwise, it was yeah, pretty on track. All right, that's all I have.
Yeah, thanks,
Any
Minjang.
questions? Yep.
So let's see if we have time for questions later, Minjang. Let's start with
Yep.
Jianhui's presentation.
Can you guys see?
Yes, I can see it.
Okay, great. So just a brief update on Intel GPU backend. I only have 2 slides. One slide is the status update, and then the other is actually questions. So on the status side, we have been focused on improving GM performance. So this is a great result that we achieved that we would like to share with the community. So basically, we are able to achieve 90% above against the expert tuned kernels. So the shape contains like a 3 dimension. There's a batch dimension, and then there's M and K, and it has both compute intensive kernels and then memory bound kernels. So we are glad to see both. We actually can achieve very close to what the expert tuned kernel can do. So the data is tested on Intel Max Data Center Max GPU, also known as PVC, and we are working on expanding this GM on broad set of shapes and looking to some advanced algorithm like a split K, stream K, and also looking to flash attention, things like that. So one thing I would like to notify the audience is that our implementation is really fully reuse the upstream implementation. So the backend actually now we switched from previously SPIR-V dialect to LVM dialect, and also use the SIMT flavor. So that allows us to reuse all those lowering passes from GPU Triton GPU down, and also a bunch of Triton GPU optimizations. So that in order to use the Triton GPU optimization, we actually extended the DPass layout. So to cover extended the dot layout to cover Intel GPU. The DPass is Intel instructions name. So basically, we have a layout specific for Intel's dot operation, and based on that, allows us to kind of plug into this Triton layout-based optimization including like a coverless or layout propagation, layout removal, and we also utilize that the Triton pipelining, software pipelining design to implement the prefetch for Intel. But like all this performance currently are achieving on top of the block pointer programming model, because underneath our hardware, it requires the 2D block loader to get the best performance. If we just using tens of pointers, then we go use a generic loader that does not give best performance. Then we have to use this 2D block pointer to get performance. So yeah, any question on this slide?
Just pointing out for the audience, another difference is that we're not loading into shared memory like it's done for NVIDIA for the operand of the dot operation, because our hardware allows us to load directly into cache and then registers. So that's one difference, that basically we're not exploiting shared memory at all at this point. And that's just an hardware, just due to the target GPU hardware differences. And yeah, like Jen said, we do heavily rely on the 2D block, on the block pointers.
Yeah.
So does that mean you rely on L2 for like reuse instead of using shared memory?
In the current hardware, we do not rely on L2. The prefetch is prefetched to L1, shared by multiple subgroups.
I see.
Yeah.
I'm a bit curious about the block pointer thing. Is it because, so that means your pointer needs to be uniform basically?
Correct.
When you do a block load?
Yes, you need to set up this like a block pointer in such a way it's a uniform, and also it just you cannot give a bunch of offset. Just give that what is the start of the offset and what is the stride, what is the size of the block.
Oh, you need to give this. Okay, that's right. Yeah, that makes a lot of sense. Why block pointer? Interesting.
So yeah, so our hardware does have some unique thing, including this block pointer and also the prefetch going through L1, as Itor was discussing. But we managed to reuse the upstream implementation as much as possible. So that we kind of like prepare us into the future upstreaming as much as possible in terms of engineering technical decision wise. So the question is really about the programming model, because right now we are kind of hinging on this block point a lot, but we see from the kind of code example you guys has been removing the block pointer, and also in the code internal process you kind of rewrite the block pointer back to the regular, and also you're adding something called the TMA descriptor. But meanwhile, you're also saying TMA descriptor is not is experimental. If you just look at the TMA descriptor, it is more general. It's it's from the language, from the parameters it passes. Underneath probably just the code CUDA thing. But from the language point of view, it's just to describe the original tensor input tensor shape, element type, strides, those things, and then the only difference is then this block pointer is that you quit this thing on the host side. We would like to get some guidance from you, like how you view these two things evolve, like what will be the main thing you would visioning that like a future Triton programming on GM would be.
yeah, I can try to answer some of it. So Phil is not there, but hopefully I'm not saying anything wrong there. So two things, guys. So TMA descriptors, indeed, is pretty different than block pointer. So historically, block pointer was originally added in the hope of mapping to TMS. Turns out it doesn't map well, and we've not been able to use block pointer to represent TMS. So now there's this experimental TMA descriptor, and it's mapping more closely to TMA. And one of the big differences is that those descriptors, they live in global memory. So plans we have for the near future is one is we are planning to move the TMA descriptor from experimental into the extra.CUDA namespace. So it will become some kind of like CUDA specific thing and move out of experimental because basically we have not been able to find a better way to represent TMS. Block pointers. So far, we were originally planning, and we're still kind of thinking of deprecating it, mostly because again it was originally meant for TMS. I think your use case is definitely interesting, and I wonder if it sounds very similar to like maybe use case the CPU would have, although I think the fact that you have a stride makes it a bit different. So that's the future of block pointer is not super clear at the time, unfortunately, and yeah, it would be hard for me to predict what's going to happen. Yeah, I mean, I do wonder if you could get away with different solution, but I don't know enough of the details to comment on that.
Yeah, as far as understand, so sorry, Casio. Like people who have this accelerator type also interested in the block pointer. Are you still under that? Do you get the similar impression? Like people would like to see this block pointer type of programming.
Could be, yeah, I guess. But the hard part is, and yeah, I think AMD was also thinking maybe that could help them. I guess the one challenge is whether we can get to a representation that works on a bunch of hardwares, and that's been the challenge, right? Because for instance, it just for TMS it just doesn't map well, and you're not able to fit it into the block pointer programming model. We have to see if I think if a bunch of hardwares definitely map well to block pointers, then it makes sense to have it. But if every kind of hardware needs its own things, then we defeat the purpose of portability, which is a big goal of Triton.
Yeah, I think I know that you guys are very busy with TMA, but I do think that making sure Triton ecosystem to use a one common way to programming GM has lots of value.
Of course, yeah. I understand. I mean,
yeah. I think I don't know whether you guys think about this, like make this TMA descriptor more like a generic interface. Because right now, if you look at the programming model, it's just to create
it's
something.
very hard, right? I don't think you could make it portable. That's one thing I was trying to do for quite some time, but I don't believe it can be made portable. Mostly because again, the data in the TMA model, they live in global memory, and that means if you're trying to use that for a GPU that doesn't work that way, where like the descriptor or the tensor lives in a different place, you're not going to be able to have an efficient lowering. And something, if you go with block pointer and you try to use TMS to implement block pointers, you're not going to be able to have an efficient implementation.
Yeah, I don't fully follow this point.
Which one?
Yeah, you said it, like the TMA descriptor like probably harder to be used by other hardware.
Yeah, it would be right, because basically you would have to represent basically the descriptor is created separately. And that means if you wanted to use that for another GPU, the GPU would first have to, like, let's say you have a something like your 2D block pointer. You would have to first load the descriptor and extract the information you want out of it, and then do your 2D
That's
block
good.
pointer, and that
Yes.
would be very inefficient. Does that make sense? So I mean, it would
No,
be,
it's actually we want to see how it works actually. So like the overhead on our side is really to load this TMA descriptor now created by ourselves, and then it's just a global memory load additional, and that's
yeah,
one-time cost. Yeah, it's a one-time cost. It's outside the K loop.
I mean, that's true. If you think you could fit it into like the kind of descriptor programming model, then yeah, there may be an opportunity to then have something portable, and then that's that would be actually quite a nice solution. But
yeah, the other one is I don't know, like, is the community, has anyone working on this try to kind of like annotate this tensor pointer so that we can convert? I know Ian has been working on this using more like automatic compiler optimization analysis, just going back. But the other case is like modular case, like you cannot really fully recover. Any thought along this line, and or
so you mean start from a pointer representation and try to get
recover?
to
Yes.
a tensor point, a block pointer. I mean, there are definitely cases you can pattern match it back, but it's not always true, right? And
Yes.
if you look at like many of the kernel examples we have, it's not going to be possible, because just when you use pointers, you're going to do something different. And if you were to use tensor of pointers, one thing we were suggesting people to do is to rely more on the alignment analysis and I think that was a suggestion for the CPU backend, and I wonder if that's something you've tried. And it's very much possible that the alignment analysis as it is now is not powerful enough, but maybe one path would be to improve the alignment analysis to be able to handle those kind of cases.
Yeah, we're internally exploring this route also. So if just wonder whether there's like other team in the community also like try to make this path more robust, that actually also will be very beneficial.
I haven't been following it a lot, to be honest, all those different projects. Maybe I think the CPU backend is probably one that would have similar needs, but again, I haven't followed closely the development there.
Yeah, could be a potential future topic. Yeah. So just for next two questions, really about the upstreaming our like some code changes we made on our side. Those are, we think, would be beneficial for Triton. Like we also in the Triton CPU side, the Minjin was mentioning that the Triton GPU lowering is the last step, is a gigantic step, just lowering from Triton GPU to LLVM level. If we kind of like a refactoring, and it would make it multiple passes so that the logger can print more fine-grained steps, that could be helpful. And the other thing is that along the journey, we make Intel GPU work on enabled for Triton, we found that Triton GPU itself could be some implementation right now. It's really hard coded for NV and AMD, and so if you guys open to it, we would love to make it more generic.
Yeah, I can also actually try to answer those as well. So the first one, I agree with you. The lowering from Triton GPU to LLVM is a very big jump in abstractions. In my experience, it's pretty hard to find a good intermediate representation, and the cost of it is going to be high. But I mean, definitely willing to listen to ideas and to
No, maybe there is some misunderstanding. What we mean here is not to introduce another level, to introduce more gradual lowering to different dialect, although that is a good thing in general. It's more like that there is the path that convert for Triton GPU to LLVM. There is it encapsulate a bunch of other passes, and so if you want to debug it with print MLIR debug print before or print after, if we do not encapsulate those passes into a wrapper pass, then the MLIR infrastructure would allow you to print the IR after each one of the transformation more easily. So that question is about that part.
Yes.
What paths are encapsulated in the lowering?
It's the path that converts. Essentially, he adds all the transformation and he tries to convert to generate the final LLVM dialect in MLIR.
Oh, you would want
It's
okay. I understand.
basically, that pass is almost like a mod, like a pass that calls out many other transformation that could be called directly instead of going through it. And
like for example, memory up to LLVM, make range up to LLVM, assert up to LLVM, control flow, all that is all mapped in one single transformation.
I see. So you're saying you would want to break up the conversions into several passes.
Yeah. So essentially, it's a non-functional change. There would be no changes, but it just it allows a little bit more internal debuggability in the sense of developer working on Triton can see the IR before and after every single step, every single transformation. More easy.
Yeah. Okay. I understand the question. And I think, I can see why that would be easier. So I think there's a bit of history there. It's first in MLIR, the convert layer, those conversion passes had to be monolithic. I think now they've improved, and you can basically, they have this thing called unrealized cast, and you can break it up, and basically it's just the conversion will because the prime is those passes, it does those type conversion, right?
Mm-hmm.
So in the type conversions, it makes the type inconsistent between def and uses. So I think now there's those unrealized casts that will basically glue the different patterns, even if they run in different passes. So that would be technically possible. I think one downside is that the way the conversion path works right now is you still have the opportunity to pattern match when you're in the lowering, in the sense that you still have access to the original IR, which is all in tensor. And that's not something we use very heavily, but we have few patterns actually that rely on that, where you can actually look around and make a decision, which I agree, it's not super useful and it tends to be not a great thing to do, but we do have a few patterns that rely on that. So that could probably be worked around. I guess that's one downside. The second downside I can think of is that means you'll have an intermediate IR that mixes two different abstractions, right? One being the tensor one, the other one being the CMT one. So that may also be a little confusing. But I do understand the advantage of being able to break up the pattern. So I would have to think more about it, but I understand it. But I think there's a few downsides to consider.
Yeah, no, we have not done anything concretely. We're just like, oh, maybe this is something that, and I have heard from, I mean, I think on the CPU as well, it would be more useful too. It'll be useful for the people working on the CPU as well.
It's possible. I wonder if we can make it like a more like a debugging mode, or I don't know. I need to think more about that. But yeah, that's a good point. Yeah.
How about the last one? Like we do have.
Yeah, I think it's going to be a case by case thing, in the sense that, I mean, yeah, I know in the past we had patches that would add things. I think the argument is, oh, this is more generic. But at the same time, if it's code that we don't need for any of the backend upstream, it's going to be a tough sell, to be honest, to upstream those. But again, I mean, I think it's hard to come up with a general rule. Unfortunately, I can just give you a feel of, like, yeah, some stuff. If it's a cleanup, if it makes the code simpler and it makes it more generic, sure, I think we would accept those patches. If it's adding logic that sure is more general, but basically add cases that would never happen for any of the upstream backends, I think the preference would be for those to live downstreams. I know it's not, I don't have a super clear rule, but hopefully that's a good rule of thumb.
Yeah, I think it's like on the layout analysis side, I think some of them, I heard that from team that we want to be make some change.
Basically, a lot of the TTGIR transformation uses the different data layout directly, and for us to reuse it, which we want to reuse a lot of the logic and transformation, we have to copy the whole file and then add the DPath layout in there, which is not ideal because we need to sync the file all the time and so on.
Yeah, okay. That I think we can definitely get away with interfaces, and I think people have been adding already, like, I think actually quite a few of those patches came from Intel, interfaces to basically abstract those special case away. I think in general those would be acceptable, yes. Like for instance, the DPS layout, I'm guessing, is very analog in general to the MMA layout, and you can abstract. I think there's already an abstract MMA layout, or if there's not, it can be added. And,
okay, so extending the MMA, like the base trade or interfaces, is welcoming changes.
I think, yeah, in general, as long as it's reasonable, I think, yeah, we would accept those changes.
So does it mean that we don't have to running this CI on Intel GPU, but we could extend it adding Intel DPath layout to the. So I just want to really understand what you're saying. Like you're saying, like we could just upstream the DPath layout.
No, that's not what I said. I said if some of the passes you want to reuse, but there are hard-coded layouts in there that prevent you from using them. I'm saying you could we could replace those hard-coded uses by interface, like basically
interface.
Some new,
okay,
like,
I see.
Interface.
Okay.
And to make the path, yeah, more generic and not hard code, like, oh, this exact hardware layout.
Okay, got you. Yeah. Yeah, that's what we was thinking along this line.
And I have a comment on one of your comments earlier, Thomas. A concern for because we are now heavily rely on block pointer to get good performance, and it sounds like there's a possibility of it getting deprecated. Like, should we worry that one day we wake up and we merge from upstream and it's gone?
No, I mean, I'll make sure we give you a heads up, or we like, to be honest, we've not been thinking about it at all, and I'll check with the rest of the team, and definitely we'll make sure we talk about it before, and we come up with a good reasoning. And
yeah.
But to be honest, it's not a super expensive feature for us to support. So I think if there's a legit use case, we could probably consider like keeping it longer. Although I don't want to talk for Phil. He's going to have the last word there.
Okay.
But yeah.
Okay, thank you, Thomas. I don't have more questions.
Okay, yeah. Thanks everyone. We are over time, but is there anything last minute anyone wants to ask or comment? Okay, if not, thanks everyone. So a quick update is there's a Triton conference next month. So if you haven't seen Phil's message on chat, please look at that and please register if you're interested. We won't have a meetup next month because we'll have the conference, but we'll see you again in October. Thank you. Bye.
Thank you.
Thank you.
Thank you. Bye.